Hello there, and welcome to the first video in the How the Bifrost Works series. Before we get into the details of how each component works and its particular implementation, I thought we should first examine how a CPU works at a high level and see how this design is reflected in the Bifrost. A CPU's main task is to read machine language instructions and execute them sequentially. Therefore, the CPU in effect implements a very simple loop: fetch the next instruction on our program, execute it, and repeat until the program is done. Let's take a look at how this loop is implemented. Our program is stored in a region of memory called the instruction memory, which is inside the CPU. The CPU needs to fetch each instruction in order to execute it, so we need a program counter which points at the current instruction to know which instruction we need to fetch. When the computer is turned on, the program counter is set to 0 so that it points at the first instruction. To fetch that instruction, the CPU reads the first instruction from instruction memory and stores it in an instruction register. Now that we have the instruction, we need to break it into its relevant components. As we can see here, an instruction is composed of several parts: the opcode, which specifies which instruction this is in our instruction set, and other information such as any source or destination registers, constants, called immediates, and anything besides the opcode. Given this information, how does the CPU know what to do? To execute instructions, the CPU executes tiny hard-coded programs called microcodes. These are stored in a separate ROM and are composed of control signal states. In a future video, we'll explain how these microcodes work, but for now we can treat them as essentially controlling the CPU's components, much like strings control a marionette. In order to specify a particular microcode to run, we use the instruction's opcode, which points at the starting address of that instruction's microcode. Putting it all together, the full CPU cycle is implemented like this. The CPU fetches the instruction pointed to by the program counter and stores it into an instruction register. From there, the CPU sends the instruction's opcode to the microcode ROM so that it can run the instruction's microcode. Then the process repeats for the next instruction. Now, let's compare this theoretical implementation with the one used in the Bifrost.
There are a few practical details that make the Bifrost implementation a little different from our theoretical diagram, but the essence is the same. Our program is stored in this EEPROM here, which functions as our instruction memory. Here we have a program counter whose value we can see in these LEDs here. Right now it's 0 because it's pointing at the first instruction in instruction memory, and which is inputted into the instruction memory's address so that the instruction memory EEPROM outputs a value, which is our instruction at this address, and then that value is sent to these two registers here, which act as our instruction registers. The reason that we have two of these registers is that each instruction in the Bifrost instruction set is 16 bits long, but the output of the EEPROM is 8 bits long. And so to fetch an instruction, we have to read and store 2 consecutive bytes from the EEPROM, which slightly complicates the fetch process. In a future video, we'll discuss and explain how the Bifrost fetch operation works. So the opcode of instruction is stored in the first 5 bits, which we read from the low instruction register here, and which is sent to the address input of the microcode ROMs. Now, instead of having one microcode ROM like we did in the theoretical diagram, you can see that we have 3. We already know that the EEPROM can only output 8 bits per address, so that means that it can only output 8 bits at once. If we need to output more than 8 bits at once, the simplest yet largest solution is to just have more EEPROMs that store data in parallel. So we send the opcode to each of these EEPROMs, and together they output all of the control signals at once. As var 3, they're capable of outputting 24 bits or 24 control signals. We can actually see the different control signals represented by these LEDs. Each one is labeled, and when an instruction is executed, you can see which ones are turned on and which are turned off every clock cycle. So now to demonstrate the CPU instruction cycle, let's run a very simple program. 5 NOPs followed by a break instruction. NOP stands for no operation, and that is exactly what it does: nothing. The NOP instruction goes through the CPU instruction cycle, but it doesn't change the CPU's state, so it's great for demonstrating the CPU cycle. The break instruction acts as an end-of-program instruction that halts the clock and as a debug breakpoint, since you can single-step the clock out of it and continue operation. Now let's see the program running. We'll show the first CPU cycle with single step, which will let us only run the computer for 1 clock cycle. So you see that right now the program counter is at the pointing at 0, it's pointing at the first instruction. And you can see that it already loaded it because we can see right here, this is the control signal for PC Advance, which is part of the NOP instruction. All it does is tell the program counter to increase. So in more complex instructions, these LEDs are going to turn will be way more interesting. But for this program, we're only just going to see this one LED turn on and off to increase the program counter and keep the program running. So this is going to be running our first NOP. Okay, so now let's single step forward. Program counter increases, the second instruction. We see another NOP. Okay, now we're in the third instruction. Another NOP. Fourth instruction, another NOP. Fifth instruction, another NOP. And now we're at break. Now, break is actually not going to be different. You'll also see the NOP going here, but there will be clock gating. So if we just run it, it will stop at the fifth one. So now if we want to just see the program running normally, we can press reset. And here it is. We're running the 5 NOPs and then followed by break.
Thank you very much for watching. If you want to explore further into today's video topic, please check out the Bytefrost GitHub, which includes schematics and documentation. If you liked this video, please subscribe so you don't miss future videos.